They don't have a record to TikTok option. All right. Cool. So there's my psychology joke about regression. Dr. Freud up there. All right, gonna start into regression models. So just out of curiosity, who here has had some experience, like sort of course stuff that's more than just like, hey, this is it, in terms of like regression-based analyses? Abby, Johnny. Okay, so we've got some people who've done some regression-based stuff. So hopefully a lot of this is going to be familiar in terms of basic concepts. But what we're going to do, this is the fundamental building block of, I mean, sort of it's a very simple case of that, or not a very simple case of it. It's a simpler case of that general linear model. If you understand regression, if you've got a good handle on regression, the ins and outs of regression, I don't know that there's another type of analysis within the generalized linear model or general linear model stuff that you won't be able to understand and pick up. Like the fundamental concepts for anything that's not just straight means based stuff is all found in regression. So if you're a regression powerhouse, sky's the limit in terms of picking up other things, right? Like you get into Bayesian stuff and that's a little bit different. But everything else is just stronger regression based. So we're going to spend a lot of time with this, getting into the nuts and bolts of why you're going through and doing certain types of things. And again, everything that we did last semester in terms of mean based stuff, you can run it in a regression model. So this really is kind of the if you have this, you'll be in a good spot. Okay. So we're going to do a quick overview, talk about some model selection, then types of research questions. We're going to talk about bivariate regression. You'll hear sometimes, and sometimes I'll slip back and forth, talk about this bivariate regression or univariate regression. It just means regression with one predictor. It's the same thing. You'll hear talked about different ways. We'll finish up with a quick overview of multiple regression. Here's where we have multiple predictors on an outcome. Now, again, within regression terminology, you often hear people talk about independent variables, dependent variables, outcomes, prediction, and things along those lines. You got to be kind of careful depending on what field of psychology that you're working in. Experimental folks get a little bit more, tend to be a little bit more specific in terms of what we're calling independent variables and dependent variables. That tends to imply a manipulation or sort of things along those lines. When we get into regression, we get a little bit more loose with that. Anytime we talk about independent variables, just think about predictors. Outcome variables are your dependent variables, things along those lines. Okay. Also, this idea of prediction, right? We'll talk about prediction. Sometimes people get really worked up if we're talking about concurrent sort of data, right? Some people prefer to hold prediction as something, predicting something in the future. Technically, it's not. If I know something about X, can I predict something about Y? I really don't care about when I measured Y, but just note that you need to probably be careful in like developing manuscripts and things like that. A lot of times people get really dodgy about referring to predictors. Mathematically, that's what they are. Conceptually, there's some sort of tricky stuff around there, but we'll use this and sort of kind of go back and forth in terms of the language, but just be kind of aware about that. Okay. And then we'll finish up talking about some specifics of our estimators, what's happening. So, okay. So primary objective of a regression model is to predict scores on some continuous outcome. Again, remember that anytime you're looking, trying to figure out like what type of analyses do I use, know what your IVs are, know what your DVs are, know your level of measurement, and all of a sudden you're going to be left with maybe one or two choices on how you go about a few things, right? Here for a regression model, what we're doing is we're looking at the prediction of some continuous dependent variable, some continuous outcome, okay? Bivariate regression or univariate regression, what we see here is we've got a single independent variable, and that independent variable can be continuous or dichotomous, okay? We can model categorical variables. We just have to be careful. We have to code them appropriately to include, right? But in terms of your inputs, it can be continuous or dichotomous predictors, one continuous outcome. Bivariate regression is equivalent to a Pearson correlation, okay? I can run a correlation between X and Y, or I can regress Y onto X in a regression equation. The only thing that's different with the regression equation is we just get regression coefficients. Whereas in the Pearson correlation, we just get one coefficient that tells us the magnitude of those two variables, right? But our standardized regression coefficient in a simple bivariate regression is identical to my Pearson correlation. So just knowing the association between those tests, okay? And when I have a IV that's dichotomous, just a group variable, 0, 1, regress a continuous outcome onto a dichotomous variable, just a grouping variable, then I've got a t-test, right? It's mathematically, they're identical, right? I can, any t-test, I can run a regression. I can just sort of regress my outcome onto my grouping variable. The p-value is going to be identical across those two things. They're mathematically identical. Okay, we talk about them a little bit different, but they're the same test. Okay, multiple regression. Here's where we have multiple independent variables. Again, the codes that we're using, they have to be continuous or dichotomous variables. Now, again, I can have experimental condition. Let's say Allison's got experiment 1, experiment 2, experiment 3. I can model that in a regression. I just need to break those condition numbers into some dummy variables. It's experiment condition 2 versus control, experiment 3 condition 3 versus control. I can go through and do the same stuff. I just need to sort of make sure I put it in there appropriately. What you can never do is take any type of categorical variable, multi-categorical variable, and drop it into a regression model. Okay, let's say I have sort of background demographic characteristics. I have racial ethnic identity in there, right? And I've got 0, 1, 2, 3, 4, 5, 6 forever, whatever grouping variable I want to do. SPSS will not let you do that, but it's nonsensical to have in there because that's not an ordered thing that we can go through and sort of interpret, right? So just make sure that you know that anything that you're using as a predictor in a regression model has to be either a continuous or a dichotomous coded variable. Okay, and here our multiple regression, these are going to be equivalent to our ANOVA models, so long as we're coding our predictors in our interaction terms. Okay. Yeah.
You say you can model a categorical one. Could you use like the example of the demographic information to like explain?
Yeah, if I want to look at differences in some outcome across different underrepresented groups, right? And I had reasonable representation of different underrepresented groups. What I could do is set up, and let's say I'm looking at respondents, Black respondents, Hispanic respondents, and sort of Asian respondents, something like that, right? What I could do probably is if I wanted to see how those individuals were responding relative to majority culture, I would just have white people be the reference group, right? And then I would have a dummy code 0, 1 for Black participants, 0, 1 for Hispanic participants, 0, 1 for Asian participants. And then basically what it's doing is looking at differences between each one of those groups relative to my white participants, right? And then so I've got a categorical variable with 4 levels to it. But what I've done is I've broken that into three dummy variables that will then tell me sort of function, like literally my coefficient will tell me the difference between my white participants and each one of those different groups. Okay. Now, let's say I wanted to compare other groups. What I can do is start changing around who's the reference condition there, and then it's all going to start going through. So the thing there is we need to go through, at least in our regression models, you have to choose a reference. The reference group is the comparison group that everybody gets compared to, but then I can just run a different model. If I want to look at the difference between Black participants and Asian participants, I can just make Black participants the reference group, and then everybody else gets compared to that group. Okay, so have to know what you're doing and sort of thinking about how to go through it and put that together. But again, incredibly flexible model that we can sort of get at. There's nothing that I get out of a traditional like means-based analysis that I can't model in regression, and probably better, right? What we start to get into, Johnny, this will happen in Stata, right? Like a lot of, let's say I have a factorial ANOVA or something like that. I've got a violation of homogeneity of variance. which is problematic. It's hard to do anything real with that within the context of a factorial ANOVA model. But what I can do is I can model that as a regression model, use a different estimator that accounts for violations of homogeneity of variance, and I can get better estimates and tests of my associations, right? And that's even when we talked about in SPSS, if I have a sort of, if I want to account for homogeneity, a violation of homogeneity of variance, and I tell SPSS to do that, basically what it does is it models it in a regression model. Okay, so just a lot more flexibility in terms of how it go about doing things. Yeah.
Do you have like more than one reference or start with one reference and then another? Like if you wanted to start with white and compare to all the groups and then do black and compare to all the
Yeah,
groups?
you would need to go through and do that. And so it kind of depends on how you're going through. If it's important to do all possible pairwise comparisons, then you just say I have to rotate your reference group through, but it doesn't change your model, right? Because in your model, all the same data is going into the model. It doesn't change anything. It's just changing what the specific comparisons are. Like essentially what you're doing, you're just running post hoc comparisons up with that, right? Except for in the regression model, it just gives you, and we talked about in ANOVA, Helmer post hoc, where you just compare all categories with a reference group. That's essentially what it's doing. But I can go through, and if I understand how the model is working, and that's what's cool about this, is I can bend it to my will and make it tell me sort of whatever I want it to tell me with that stuff. Yeah. Questions? All right. So classic objective of regression is prediction. Okay. Regression was developed late 19th, early 20th century, right? About like, oh, kind of what's going on with this stuff. And the idea was to be able to predict some outcome. Hey, if I have information, can I specifically predict a point estimate, or sort of can I predict what's going to happen in the future? Well, we tend to not worry so much about predicting something, but using it for different types of questions. So we can sort of put together, and this would be consistent with a classic approach, want to know how well our regression model predicts some scores on outcome Y. Okay. And here we're just estimating this with our R-squared statistic, right? Our R-squared statistic tells us how much variability in my outcome are we accounting for with the model. Okay. If our R-squared is really high, what does that tell us about the predictive quality of our model? It's good. If it's really low, what does it tell us? Or yeah, our model isn't telling us much about the outcome, right? Now in psychological science, we're rarely, some areas, if I'm in econ or sort of marketing or something like that, my main goal may be to maximize that R-squared. Because if that R-squared is really, really high, it's telling me I have a good predictive model. I can reasonably forecast what's going to go through and happen down the road. Now, in psychological science, we're rarely worried mostly about sort of maximizing our R-squared. Are you generally using this more to test some theoretical association, right? But we'll get into this a little bit later on. It's always important to remember that the maximizing, sort of increasing the quality of my predictive model helps with my power. I have a much more powerful test if my regression equation is predicting a lot of variability in my outcome as opposed to little. Because the stuff I'm predicting, okay, this is the stuff I've predicted. What do we call the stuff that we haven't predicted? What's the variability in the outcome that I am not able to account for? What do we call that? Error, right? I don't know what's going on there. It could be predictable. I just don't have anything in my model that does predict that. And when we've got error, where does error go in our statistical tests? If you're looking at a t-test, where does error go in that equation? It goes in the denominator, right? Your standard error down in the denominator. What happens when my denominator gets really big? What happens to the outcome? It goes down. My denominator is really small, goes up, right? And so we think about if we can shrink that error term, it gives us more powerful tests, right? And so even though our goal in psychological science is rarely to maximize my predictive value of my equation, it's still something to be mindful of, because if I have things, as long as I'm including predictors that are additive and not redundant with everything else I've got in there, what I'm doing is I'm increasing the power of my tests. So again, something to be thinking about. So the null hypothesis here is that my R squared, my population R squared is 0 here. Okay, so basically saying the predictors I have in my model tell me nothing about my outcome. Okay, we can also ask what's the unique association of variable X with outcome Y controlling for other variables in the model. Okay, after I pull out all the shared variability, everything that's sort of accounted for by my other predictors, what's the unique association between this predictor and my outcome? Here we're measuring this with our regression coefficients. Beta is our standardized regression coefficient. Our null hypothesis is that this predictor has no unique association with my outcome after I control for other stuff in the model. Last thing that we can do with our straight up regression, what we can start to do is like start talking about incremental contribution of variable X or set of variables to the prediction of an outcome above and beyond stuff that's already in the model. Okay. Here, we're estimating this with a change in R squared. Here's where we start to get into hierarchical regression models. Okay, I'm saying, let's say Gabe has in his area, everybody knows what are we trying to predict, Gabe?
Stuff, I don't know.
Yeah, what kind of stuff? Tell me something interesting.
That's the thing, I'm blanking out.
They're gonna do
What are we trying to predict?
Whether or not people are, wait, hold on, give me a second. Whether or not people will actually study for the exam.
Okay, study time. We're experiencing study time, right? So the like hours spent in preparation, right? And so we can go through, we can think about like based on a theoretical model, we know that sort of intrinsic motivation, prior ability, sort of like stuff like we've got like a whole set of predictors, right, that are going through, and we know like from our theory said like these are the things that predict sort of effort towards study and things like that. But Gabe instead has an idea of like, yeah, that's good, but I think they're what these theories are missing are this other thing or a couple of different things, these other variables that also account for stuff above and beyond what we've already done. Here we've got a regression model where maybe Gabe goes through and measures study time that people sort of have gone through and engaged in, and then Gabe's also measured all the things that are included in our major model of sort of whatever study time, but then he's got a couple of novel variables that he's gone through and taken a look at. And what we can do is we can sort of set this regression model up to say, okay, how much variability in study time is accounted for by these 5 things that are sort of well established. Everybody knows like you're a dummy if you're doing this research and not considering these things. But then what we can do is then in the second step, layer in the 2 variables Gabe has specific interest in to see does the inclusion of these 2 additional predictors add do I have evidence that this adds to the predictive validity of this model? Yeah.
Why aren't you using R squared for that?
Well, it's just changing R squared.
Okay.
So literally all we're doing is we're looking at the R squared with the full model, and we're looking at the R squared with just the theory-based predictors and taking the difference between those R squared and seeing out whether if that value is something that's not 0. Okay. Yeah.
I guess I'm having a hard time understanding how that's different than the second one, like the unique contribution.
Oh, here, hold up real quick.
Oh.
You signed out.
We're recording.
Are we still recording?
Mhm.
Okay. Whatever. Okay. Yeah, no, that's a good question, Abby. And here, with this, we're looking at individual predictors. Okay. And we're looking at like sort of what's the unique contribution of this predictor, this predictor, this predictor. Here, what we can do is we can start modeling sets of predictors. Okay. But what you keyed on is and when we start talking about estimating effect size in here, sort of recognizing sort of the contribution of individual predictors to your R squared and how that all fits together is going to be really critical in understanding what's going on with the model, how to manipulate it to get types of answer the types of questions you're wanting to. Okay. Yeah, Olivia.
This might be a dumb question.
It's probably not. You're all hopped up on pain meds.
That's what, so this might not be coherent. Or it may be not relevant. Is that P in the first null thing?
Yeah,
Supposed to
that's-
be the equivalent of R?
Yeah, that's the Greek notation. I'm can't remember off the top of my head what that symbol is, but yeah, technical notation, it's I think it's rho. I think it's capital rho.
Oh,
I'm not sure. I was never in a fraternity or sorority. So.
But that's equal to R
Yeah.
squared.
Oh, well, R squared. I mean, it's
Okay.
sort of same.
okay.
Yeah, good question, Danielle.
So this is hierarchical regression. So with
Yeah.
the example you're saying with Gabe, you're putting in that important stuff, like with the test, whatever stuff, the stuff that is in the literature, and then you're putting the stuff you're interested in last?
Yeah, that would probably be the way we
Okay.
set it up, but we'll get in and talk about like how you go through and look at this stuff. And this will start to get into when we look at moderation models, things like that, how we start to go through and put things together. Thing is, hierarchical regression is not special. It's not magical. It's really basic. Some people think it's magical and special and tell you you have to do it. You don't. It's all it's doing is a simultaneous thing. But different people learn different things by tradition and things along those lines, but we'll go through and talk about kind of what it does do and what it doesn't do. What it does do is pretty minimal. Our hierarchical regression will give you an R squared change test. And that's it. That's the only thing it does that's special. So if you need that, that's awesome. If you don't, then it's sort of inconsequential. But we'll talk about when you might want to model that stuff in. All right, so let's get into bivariate regression or univariate regression, whatever you want to call it. Basically, we just got one predictor. And let's say we've got a group of 100 students out there right now. I gathered them. They're out there being very quiet because I've been told they had to be very quiet. And outside, we know that that collection of students, you can't see them, hear them, anything like that. You know that the average weight of those students is 150 pounds, okay? If I go through and randomly grab one person, right? And I'm sort of out in the hallway, I'm like, hey, I got this person here. How much does this person weigh? Lindsay, what is your best guess statistically, absent any other information?
150 pounds.
150 pounds. Are you gonna be right?
It depends how much variability there is.
Yeah, that's a good answer. It does. But how confident are you that this person weighs exactly 150 pounds?
I don't know.
Probably not very confident, right? But did you have a better guess statistically than that 150 pounds? No, I can guess something else. I can guess something else, but I'm gonna be more wrong at the time than just guessing the mean. Okay. So what if, okay, I grabbed somebody else, I got a different person, right? I'm like, Jalen, I got a new student here. How much does this person weigh? This person is taking 13 credit hours this semester. What is your best guess for the weight of that randomly selected student? 150 pounds. Why? I gave you extra information. Like, why aren't you adjusting your prediction based on the information that I provided you?
Cause that extra information isn't something like physiological, like it doesn't tell me anything about their body.
Yeah, right. Probably not. I mean, I could have some hypotheses about how sort of stress and sort of credit hours might impact sort of mass or something along those lines, but that'd be pretty far-fetched, right? Basically, I've given you information, but it's not information that's relevant or has any sort of predictive power in determining my outcome. Okay. Kate, I grab another student. I'm just grabbing random students out of the hallway. I'm like, hey, I've got a student. Tell me how much they weigh, and this is how tall this student is. Now, all of a sudden, what's going to happen to your prediction on their weight?
I might cite to kind of factor in a little
Right.
bit,
If I say this person is 6'8", what are you going to guess?
but they might be a little over 150.
Yeah. If this person is 5'1",
Might be a little under.
under, right? So, and is that a good basis for making an adjustment on your guess?
Yeah, I guess. so.
Yeah, probably, right? Those two things are not perfectly correlated, but there's a strong association. It's just physically, right, there's just more of you, and more of you in space is gonna sort of be a higher mass, right? And so what we've done is we've talked about here, including two different predictors, but we got one predictor that has information, and one predictor that doesn't have any information, at least for the type of thing that we're going through and taking a look at. And this is what we're doing with regression, right? We're going through and trying to see, can I take information from this variable that tells me something about the likely outcome of a different variable, okay? And so our goal with regression is to summarize this association between X and Y using a linear model. This is our sort of straightforward application of our GLM, okay? And our regression equation is going to give us a straight line that best characterizes that association of X and Y. Okay, now we talked about same thing with correlation. Talked about the GLM as a general linear model, right? So we're measuring linear associations. Abby, is there anything in this scatter plot that would suggest to you that a linear model is not a good fit for these data?
There seems to be some more extreme values, but overall I'd say no, the linear seems to fit.
Yeah, we've got some people who are not as tall, who are higher in mass. We've got some people here who are taller, also higher in mass. These are sort of unique observations that don't sort of are far away from our prediction line, but there's nothing nonlinear in there. Like here, I would go through and take a look and say, yeah, a linear model is not perfect, right? But it's going to be sort of an okay way to go through and model this data, okay? And so what we've got here, if we go through an estimated regression equation with our bivariate regression, we're going to have some specific numbers that are going to tell us a whole lot of information, okay? Form of this is our y hat. This is our predicted y, okay? Predicted y, these are all values that run along this regression line, okay? Are these y hats, are these actually observed scores? No. They're model implied scores. Based on your height, this is what our model predicts, says that you should weigh. Now, what you actually weigh is a completely different situation, right? Always, always, always remember that these are predicted values, okay? So these are only good as our model. If our model is accounting for 5% of the total variability in mass, I shouldn't have a whole lot of confidence that these are going to be super accurate. If I'm an R square of 0.95, this is going to be pretty close, right? So always remember that these are model implied values and not observed values, okay? So this is my predicted score, my expected value of y. Keep that in mind. That's a sort of a term that we'll go back to. Here, A, this is my intercept or my regression constant, okay? What this is telling me is my predicted value of my outcome when X is equal to 0. And if you just think about, like I was literally looking online, is like refreshers in algebra. I don't know. Who here is feeling rusty in algebra? Okay.
I hate algebra.
Yeah,
It
yeah.
was like my freshman year of college.
Okay. Like I'm just saying this, like I went through and there's like tutorial that's just like, and it was like a 50-minute video, like just on refreshing algebra. It might not be a bad thing to go through and do that because like for the next several weeks, particularly when we get into moderation, all we're doing is algebra. So it might be worth going through and refreshing. But if we look at my equation here, right? I know that sort of A is my intercept, my expected value of y when X is 0, and this makes some sense. I'll just, I guess, sort of spoiler, my residual on average should be 0, so that falls away. If I throw in 0 for X, B goes away. What I'm left is A equals Y, okay? So when my predictor value is equal to 0, what is my expected value of my outcome? This is what my intercept is telling me, okay? Now in psychological science, we don't pay attention to the intercept a whole lot. What my expected value when Y is equal to 0 may not mean something. It might not mean, or when X is equal to 0, it might not even mean anything reasonable if a 0 value for X doesn't make any sense, right? If I'm predicting weight based on height, what's my expected weight when someone's height is equal to 0? That doesn't mean anything, right? So, but thinking about what are my variables, what do they mean? Because there's some ways that we can start to, and we will do this in moderation, where 0 starts to become a very, very important value, and we'll start to change what 0 means for these variables in order to augment analyses and interpretations, okay? B, this is my regression coefficient. This is just my slope. My unstandardized regression coefficient is telling me very literally the expected change in Y given a unit change in X. So if I increase my predictor by 1 unit, what's the expected change in my outcome, right? Does it go up? Does it go down? Okay, my coefficient here, X is my observed value of X for case I. We're gonna be doing a lot of subscript stuff. That subscript is just saying for this individual, okay? So this is just saying, what's my predicted value for Daniela given this and Daniela's value for X and whatever error term Daniela has, right? So don't get thrown off by the subscripts. It's just sort of noting that basically I can switch this in for any observation I have in my sample, okay? And then down here we have our residual. We don't see this at the end of regression coefficient or regression equations because we're gonna have an individual error for every prediction or every case that we have in our set, okay? Mesa, what is the error term going to be for this observation based on this equation? Is it gonna be a big error or a small error for this observation?
I think a small error,
Small error, why?
because it's closer to the line.
It's close to the line, right? We did a good job. This model does a pretty good job of accounting for this person. Mandy, what about this observation right here? Am I gonna have a big error or a small error? Big error, pretty big error, right? Like my predicted value, my model says that this person's mass should be this. Instead, it's this. Our model hasn't done a good job of accounting for that person, right? I've got a big error, but by definition, my regression model, the sum of my errors will be equal to 0 for these data by definition. I've got sort of the aggregate of all this versus the aggregate of all this. The sum of my errors equals 0. And so this is a 0 term in my regression equation. Now my individual error terms for individual observations, some are going to be positive, some are going to be negative, but if I add them all up, they're going to go away. They're going to be 0. So we don't have that. You won't see that error term included in a regression model unless we're talking about some theoretical sort of properties, estimated properties, things like that. Okay. The residual is calculated, and keep this in mind because this is important when we get into some screening stuff. Your residual is calculated as your observed value minus your predicted value, right? So here, if I'm overestimating, I'm going to have a positive residual. Here, if I'm underestimating, I'm going to have a negative residual. This is going to start to become important when we get into screenings and thinking about this stuff. I've also asterisked this. This is how we calculate our residual with ordinary least squares, which is our big sort of internal combustion engine for most regression models. But there are other estimators that we can use and under certain circumstances that have better estimator properties. But for basic OLS, and OLS is a fantastic tool and does better than most things under most considerations, this is how we're calculating our residual. Yeah, Johnny.
So with the like residuals and the assumption that the sum of all my errors should be 0, is that why in the plot of the residuals in our like assumptions, that's why it should be balanced across the line of 0?
It should be. It should be. It won't always be, but it should be. Okay. So, and we'll talk about that when we get into. We won't get into that until next week. But yeah. Okay. Hopefully, what we see is a distribution of our errors that's nice and normal, right? Centered on 0, most of our stuff is pretty close. Some high, some lower. But there are situations where that might not be the case, and we need to be aware of certain implications of that. Okay. All right. So, most common estimator is our ordinary least squares. Okay. When I'm going through and I'm trying to solve for values for A and B with my ordinary least squares, this is determined directly based on sort of this residual. What I'm trying to do with ordinary least squares is minimize for the entire set the difference between my observed Y and my predicted Y. Okay. And so this is getting into some Calc 2 types of stuff. We're looking at tangents and things along those lines. But what I'm doing is I'm trying to put together a function that minimizes the sum of the squared residuals. Now, if I just added up all the residuals, I get 0, right? But if I go through and I take the square of those residuals and I go through and take a look, what I want to do is minimize that value. Okay, so let's see if we go through and take a look, and this is actual data from my Gen Psych class at some point. Here we have, I'm trying to predict midterm exam based on score on quiz 1. Okay. Overall, what type of relation do we have here, Allison? Linear. Is it a good association? Pretty strong. Like if I know what you got on quiz 1, for lots of different reasons, I probably have a pretty good idea of where you're gonna be about on this midterm, right? And so my X down here is quiz 1, here's my midterm value, okay? And if I go through and I calculate to actually regress, anytime we're talking about regression, this is a little weird, it seems kind of counterintuitive. We talk about regressing our outcome onto our predictors. It seems like it should be the other way around, we're regressing our predictors onto our outcome. No, we regress our outcome onto our predictors. So here we're regressing midterm score onto quiz 1, okay? And if we do that, we get a regression equation, 23 point about 24 plus 0.6x, okay? And so okay. So looking at this equation, what would be the expected value on midterm if someone got a 0 on quiz 1?
They got a 0 on quiz 1, what would be their expected value of the midterm?
Yeah. Well,
Plug in 0 x.
That's what I was thinking. So 23, it'd be like almost 24.
yeah, that's 24, right? So, yep, I mean, if I just plug 0 into there, all I'm left with is this, right? It's just our intercept. What's the expected value of my outcome when my predictor is equal to 0, okay? Now, these are multiple choice exams. No one could literally get a 0 on this. Like if they did get a 0, clinically, I would say you threw that intentionally. You knew what the right score was for every single answer and you deliberately chose the wrong one, right? Plenty of people sort of score at random on that, like that is indicative of milligram. And so very clearly no one sort of got that low, but and so here we could sort of have an argument about whether or not a 0 score is a meaningful, like valid score, right? Abby, what's the expected change in my midterm score for each unit increase in quiz 1 score? 0.6. So for every unit increase, every point increase someone gets on quiz 1, I would expect a corresponding about a half a point increase on my midterm exam here, okay? And so if we go through and take a look, so this is our prediction, right? But it's not perfect, right? We have some people who we underestimate, some people who we overestimate, right? But maybe I go through and I take a look, and even though I was in Josh's class and he told me that this is the best line you can get, I'm like, that guy's a bozo, I can draw a better line, right? And so I go through and I'm like, I like this is kind of catching this bottom, right? I can go through and draw that line. And so what I've done here is I've just changed the intercept, right? It's the same slope. I just sort of dropped down my expected value. I'm like, well, if someone gets a 0 on quiz 1, I don't know that they're going to get a 23. I think they're going to get a lot worse score. So I'm going to change that. Well, if I do that, now I've got a new regression line, but I'm worse off. My residuals, I'm farther, it's a worse predictive model than what I had before, right? And same thing, so okay, I don't like that, but okay, I've got some scores up here, right? I wanted to sort of get a little bit better predictor because I was off here. So I'm now increasing the intercept. I was at 23 and now I'm gonna add some values to it, right? I've done a better job of predicting this value, but I've done a far worse job of predicting this other value, right? So I say, all right, well, changing the intercept doesn't seem to be doing much, but maybe I can sort of tweak this. Maybe I can shift this up to get that. Because what I'm really concerned about, for whatever reason, is these two. I want to really make sure that I'm getting those. So maybe I go through and I sort of just tweak that just a little bit, right? Well, if I do that, now I'm doing a better job of getting this, but I've made that worse. Same thing, if I go through and do the other way, I've got that better. this one better, but I've made that worse, right? So literally there is no better line that minimizes sort of how far I'm off than this regression line that I've sort of put together with my OLS estimator, okay? It's not perfect. The number of cases that I'm getting sort of right on target look like 1, 2, 3. I mean, there's 3 cases in the whole set that I'm perfectly on. What this does is it minimizes how wrong I am across the whole set. Okay, so I've got this is the most generalizable equation or solution for accounting for the linear relation in this data. Make some sense? All right. Getting into some math, you don't have to worry about this, but I just want you to be aware is these are terms that will come up sometimes as you start to get into sort of higher level methods. The solution we're using to minimize those squared residuals, or you'll hear this referred to as a loss function, right? And basically what we're trying to do is minimize the deviation of our observed and our predicted squared here, right? And if I understand what my predicted value is, my y hat, we know that y hat is equal to a plus bx, right? So if I substitute my regression equation for y hat, because that tells me what y hat is, it changes my function here. So I'm trying to minimize the function of my observed minus my regression equation squared, okay? And if I go through, use mathematics to go through simultaneously solve these, right? Or my regression slope, what I've got is a slope of these data, right? So my regression slope, that is I go from here sort of down to here. At some point, I'm going to hit an equation that minimizes that loss function. This number will be the smallest it can be. As I start increasing it, it's going to go up the other way. If I decrease it, it's going to go up the other way, right? And so this is what we're trying to do is minimize this function. We want the sum of our squared residuals to be as small as possible, okay? And consequently, what happens when we solve for this, we get, we find that B, our regression coefficient, or, and this is for a bivariate correlation where we just have one, or regression where we just have one predictor. My covariance between X and Y over the sum of square, or over the variance of my X, this gives me the value for my unstandardized regression coefficient. A then becomes equal to the mean of Y minus my regression coefficient times the mean of X. And now I've got my expected value of Y, okay? So what happens is, even though this looks like a fairly complex math problem, right, involving higher level calculus, what we find at the back end is that our optimal values for our intercept and our slope are a direct function of my mean, my variance, and my covariance stuff. And this is all stuff that we've already gone through, worked with, we know what it is, so we don't have to be, have a recent calculus class in order to go through and solve for this stuff. Okay. Questions about this?
I get the concept, but that thing doesn't make sense to me.
Yeah.
Like, I understand that we want to make sure there's not like
Yeah.
really large.
So sort of in simplistic terms, basically, if I were to go back to this regression equation where I've got 0.6 as my value for B, 0.6 is right there.
Yeah.
Okay. If I make that 0.7, 0.8, 0.9, what ends up happening is the sum of my squared residuals gets bigger and bigger and bigger.
Okay.
If I go 0.5, 0.4, 0.3, same thing, some of my squared residuals gets bigger and bigger. So it's just, this is just the function for this B coefficient.
Mhm.
And here is the best version of that I can get. Anything else any other messing around with I do it just makes things worse, okay? And so that's the minimum of that loss function. Okay? And again, you don't need to worry about this necessarily, but I do want you to know functionally what's going on with our regression and why we're getting the values that we are. So one, that you don't think that it's just magic. And then two, when you get into other literatures where they're talking about sort of the efficiency of estimators and sort of how it works and stuff like that, this is kind of the concepts we're working from. Other questions? But if we just have a bivariate regression where we just have one predictor, easy for you to go through. You can literally calculate your regression coefficient, so long as you know the covariance, the variance, the means of X and Y, and you can go through and calculate that on your own. Foreshadowing in terms of where you're going with this stuff, right? Okay. Properties of ordinary least squares regression. Okay. If I calculate my intercept and my slope using OLS, those residuals that I get will have some very, very specific properties that by definition must be true. Okay. The sum of my residuals is going to be equal to 0. Okay. If I just add up all, and you can do this in SPSS, when you go through and you estimate a regression model, you can save the residuals. And for every case, it'll just tell you what your residual is. If you go through and add up sum all those residuals, it will be exactly equal to 0. Okay. The sum of the squared residuals, this is the minimum possible value, is what we talked about. So that minimum value in the previous slide. The sum of my observed y's is equal to the sum of my predicted y's. This is pretty cool. Again, in SPSS, I can have SPSS for my regression model, have it save the predicted value for each one of my observations. If I go through and I take the mean or the sum of my observed outcome, and I add up the sum of my predicted outcomes, those two values will be identical to one another. The sum of the products of my predictor and my error is going to be equal to 0. If I take my predictor value, my X value, and multiply it by the residual for that case and add those up, it's going to be equal to 0. The sum of the products of my predicted Y and my error is going to be 0. Okay. And the regression line, by definition, will pass through the point mean of X, the mean of Y. Okay. So you know for any set of data that you're going through and estimating a regression equation for, that regression equation, at least in the bivariate case, or with one predictor, if you find where the mean of X is and the mean of Y is, that regression line will go through.
Just to really clarify, the residual, that's the distance from like the observed like point to like the art line.
Yeah,
Okay.
yeah, exactly. Perfect. Because this is gonna, we're gonna start to get into, this is gonna start to become an important concept when we're talking about variability and where that's coming from in our model. Okay. So goal of regression is to maximally predict variability in my outcome. Okay. And this is like old school regression stuff. Johnny and I were talking about this the other day. He was asking me some questions about like, oh, well, why wouldn't we use some different modeling techniques to go through and figure out what's our best model or better model and things along those lines. In psychological science, we're generally focused on predicting some sort of theoretical relation, right? Olivia, you have some idea in your head or you're working with some model that says that this variable should hold this association with perceptions of guilt or innocence or something along those lines, right? And so your goal likely is not to maximize your ability to predict guilt or innocence. What you're interested in is, does this theory hold? In this context, are these two things related, right? But historically, the goal has always been like, hey, let's use this formula, similar to like Janan's sort of job talk the other day, right? Like, hey, how could we, what we're really interested in is like sort of maximizing how people are ability to like predict and forecast things along those lines. That was more like an applied regression type of modeling thing. Okay. And so what we're trying to do here is maximize the sum of squares of y. And the sum of squares of y is just my variability of y, right? Remember, sum of squares is a measure of variability, variance is a measure of variability, standard deviation is a measurement of variability. When we get into our regression models, we're working a lot with sums of squares, right? And that's just a raw metric. Okay. If I don't have any valid predictors, mean of y is the best estimate, right? This is my best guess. If I have some predictor that doesn't have any sort of informational value, I just pick the mean of x, or excuse me, the mean of y all day long, right? And so what we see though is the extent to which our predictors help us do better than just predicting the mean is an extent to how good our model is performing. Okay, so before, Jalen, when you're talking about residuals, we're talking about the difference between my observed value and my predicted value. We're also interested in, for my regression equation, how far is my predicted value from the mean value of y? Because if I have a regression equation with no predicted value, then my regression line is just sort of running across the mean, right? But the extent to which I start to model an actual association between there, the difference between my predicted value and my mean value start to become important, okay? Okay, so here, or I guess, excuse me, we're gonna get into sort of the deviation for the mean value and the predicted value. What we're wanting to do though, what we're trying to account for in these data is the difference between my observed value and my mean value, okay? The difference in my observed value versus my mean value, this is just my sum of squares, right? This is when we're calculating sum of squares variability. This is the deviation score from my observed value versus the mean of my sample. And I square those and add those all up. That's my variability of y, right? And so what we're doing in a regression is we're trying to break that variability in y up into a couple of different parts. Okay. What we're looking at is the difference in the mean of y from the predicted score. Okay, this is, I got ahead of myself. This is what we're talking about. This is the extent to which we can make a unique prediction for each case. All right. So I'm saying that Daniela scores a 7 on my outcome. The mean is 3, right? How far off is my regression equation for Daniela from the mean of 3, right? That's telling me how much prediction that can I get. If I don't have a good predictor and everybody gets the mean, then my mean for Daniela is the mean for everybody else, right? What we're trying to look at is like, to what extent can we make a unique prediction for all my people and all my observations in the set, okay? And this is going to be the deviation of my expected score from my mean score. But then I'm also going to be sort of wanting to break this into the difference between my observed y and the predicted score. And this is my residual. My residual tells me how accurate my score is. Okay. So I'll get into a picture to illustrate this graphically because it's kind of hard to wrap your head around just sort of thinking about it, right? Basically, take home message from this slide is we have total variability in y, or sum of squares for y, right? This is, if I'm looking at my outcome in my data, like it's the same variability that we've worked with for a whole semester, right? But what we're trying to do is break that variability of y into a couple different parts. How much can we predict? And how accurate are we with this? So I can take a look and I can talk about my total variability in y as represented by these two parts, okay? So if I go through and I take a look at some of the squared deviations of my observations from my mean, this is just sum of squares, right? Are people following me on this? People just recognize this is just the same variability. If I took that sum of squares, I could divide it by n minus 1 and get my variance. I could take the square root of that and get the standard deviation of y. This is just variability of y. Seeing that? Okay. What I can do is I can break that into the sum of the squared deviations of my predicted value from my mean. That's how much prediction I've got. Versus my observed value for my predicted value, this is my residual. Okay. If I add this plus this is what I get. Everything sums to 0 nicely here. Okay. So my sum of squares of y. Okay. This is my total variability in y. This piece, that's all the variability I have to deal with. This is all the stuff that I'm trying to predict. Okay. This is the same sum of squares that we worked with last semester in SPSS. If I just go through and select y and get descriptive statistics for it, I get my variance, I get my standard deviation. That's the same variability that we're talking about here. Then this piece here, we're calling this my sum of squares regression. This is my prediction above just choosing the mean. Okay, so if I've got a useless model or a predictor that has no predictive variability, then I'm just going to predict the mean. The extent that I've got something that does better than just predicting the mean, this is my sum of squares regression. Okay. And if I take that and what I have left over, then if this is what I can predict above and beyond just predicting the mean, what's left over? This is just my residual. This is just how wrong we are, just how much leftover stuff that I've got. Right. So it's actually not too bad. I have all the variability in my outcome, and we're going to partition this into a couple parts. How much I was able to accurately predict above and beyond just guessing the mean, and then all the stuff where I was off. Okay. So for a regression model, which one of these do I want to be bigger, my sum of squares regression and my sum of squares residual. My regression, right? So that means I've got a bigger model, and these work proportionally. As my sum of squares regression goes up, sum of squares of error goes down, right? As my sum of squares regression goes down, sum of squares error goes up. Okay, so it's just a dynamic system here. Okay, and so as a consequence, again, what we've got is my sum of squares of y is equal to sum of squares residuals plus sum of squares regression, meaning that the total variability in my outcome is the sum of my predicted variability and my residual variation. Anytime we say, so it's what I was able to predict plus error. Okay. How are people feeling about this concept?
So, okay, so the total variability in y, you could get from either adding your sum of squares residual or sum of squares regression. Which I guess is the same exact thing you have up there. Like both of those equations are essentially the same thing, they're just wrote differently.
It's all the same thing, just
Okay.
giving you different looks at it, so to kind of just piece this apart so you can see. And it's important for me to for you that you understand conceptually what's going on with these different pieces of parts. So as a consequence of all this, right, if this is all true, the proportion of predicted variation in y is just going to be my sum of squares regression, what I was predicted, over total variability is going to give me my r squared. Okay, where else have we seen a squared value that looks, what does this look like to people from our ANOVA days? What's that? Not quite F. What do we, no, that is a sort of ratio with that. What is it? Don't just whisper at me, like what?
Whispering, Johnny, you take it.
Mean squared error.
Mean squared error, that's gonna be, that's my error variability, but yes, that sort of plays in. What was it, what's our effect size for ANOVA? Eta two, eta squared. R squared is just eta squared, okay? So eta squared, so this is just, remember when in our one-way ANOVA, where we just have, variability, sort of we have 30% of the variability in my outcome is attributable to my predictor variable. Same thing, it's just an R squared value. It's the exact same thing. Okay? So again, just wanting people to move back and forth with this. But again, always thinking about my R squared, and this will start to become important as we start to sort of do more elaborate stuff with regression, recognizing this is just my sum of squares regression over my sum of squares total. This is of the total piece of the pie, how much are we accounting for? It gives me my R squared value. Yeah, Johnny.
What does eta look like again?
It's that sort of end look, remember?
Okay.
Yeah.
Yes.
All right. And so also last thing here for bivariate regression, where I just have one predictor, my R squared is equal to my Pearson coefficient squared, right? Again, because I just have one predictor, right? So if I take my Pearson correlation and square it, that value I get for that is going to be identical to the R squared I get with a bivariate regression. Okay. Again, they're just doing the same thing. The only thing with that I get if I estimate that association between X and Y in a regression model, it's just giving me a regression coefficient that tells me the expected change in Y, giving me unit change in X. If I estimate it with a Pearson correlation, it's just telling me the strength of the association on a -1-to-1 scale. But if I take the standardized regression coefficient from bivariate regression, that standardized regression coefficient is going to be equal to my Pearson correlation. Okay, there's just one and the same. It's just sort of different looks at all the same information. All right. Oh, this is a cool thing. So R squared. So we typically do, and so the most common interpretation of R squared is talking about that as the proportion of variability in my outcome accounted for by my model, right? We can also think about this. I just thought this was cool. Talking about the proportion reduction in error variability due to knowing my predictor variables. In the absence of having any predictors, what's my error variability? It's all error, right? We can think about your R squares, to what extent does that decrease error variability in sort of my outcome, right? So it's just other side of the same coin, but kind of a cool way. I don't know. I like having different ways of thinking about things that are equivalent, but just kind of a different book to help sort of kind of build that conceptual understanding of coefficients and what they mean or how we might interpret that, right? So I'm trying to predict weight of undergraduates out in the hall. How much does knowing height reduce the error variability, my error in the prediction of my outcome? All right, so we'll finish this up and then go on break. The partitioning of our regression model is similar to what we did in ANOVA, okay? And this makes sense because regression, ANOVA is just a special case of regression. Mathematically, they're identical, okay? When we're talking about our sum of squares regression, right? The ability that we're able to predict above and beyond the mean. This is analogous to our sum of squares between from ANOVA, okay? If I go through and I take a look at, well, here, let's start with this graph and this component. Here, I have a set of data, right? Here's the mean of y, my sum of squares of y, my sum of squares for my regression or for y here is just the sum of the squared deviations from the mean, right? So down here, I've got people ordered based on an x value, right? But here we've got mean of y, and we've just got, over the course of this, we've got just variability from y. This is just our sum of squares of y. This is our total piece of the pie here. Okay. Here is our sum of squares regression, right? This is the sum of the squared deviations of my predicted value from the mean of y. This is telling me how well my predicted model is working, right? So here, I've got for every single observation in this set, I've got a corresponding little block here that corresponds to where that value falls on my line here, right? So for each case, what's the predicted value and how far is that distance from just guessing the mean, okay? Here we've got a pretty good predictive line, right? We got a nice steep line. If my predictor had no informational value, what would happen to that line? It'd go flat, right? If it has no predictive value, I'm just predicting the mean, right? Here we've got a model that does pretty good. It's predicting, and so the sum of the squared deviations is doing pretty good. It's pretty big. My sum of squares regression is pretty large for this model because I've got a model that does a pretty good prediction, right? And so this is similar to the sum of squares between, okay? Think about, can anybody remind me what sum of squares between is in my ANOVA sort of framework? Conceptually what that is?
Draw the little table.
What's that?
So let me just draw the little table.
Right, you do that. Okay. Remember the sum of squares between was telling me how much, to what extent are my groups different from just the grand mean, right? If my groups aren't different than the grand mean, then I have a small f value, right? I don't have evidence of differences across these groups. But if I have new groups that are very different from the grand mean, then I have evidence of difference across my groups. Basically, what regression is doing is it's treating every possible x value is its own group. There we go. So for basically with regression, we're basically think about regression as taking ANOVA and just having infinite groups, right? For a true continuous variable, I've got a group that represents x equals 1. I've got a group that x equals 2, x equals 3, x equals 3.5, equals 3.8, 3.9, 3.95, an infinite number of groups, right? And what we're doing with our sum of squares regression is saying, to what extent is my predicted value or my expected value for everybody who scores at that level different from there, right? Similarly, sum of squares residual, this is analogous to my sum of squares within. Someone remind me what sum of squares within is within regression. Remember?
That error.
It's error, yeah. So that's good. And how do we calculate? And how do we calculate error in ANOVA? Or we're talking about deviation from the within group mean. right? So for my group mean, if my grouping variable is the only thing that determines my outcome, what should everybody's score in condition one be? Should be all identical, right? It's not, right? And so that within group deviation from the mean, that's my within group error, right? Same thing again, if I'm going through in regression, here's my line, right? Here's these little red meticulously placed boxes are sort of the expected value for each one of these cases, right? And the deviation of my expected value from the actual observed value, these are my residuals, these are my errors, right? Now, some of these errors are very small, some of these errors are very large, right? But again, if we think about regression as just being an ANOVA with infinite groups, this would be like on average, how much do everybody who have an X value of this deviate from the mean? Now, here I've made this very simple so that there's only one value for each X in this thing. But if we're actually looking at an actual regression model, we're going to have a whole bunch of people who have this same predictor score, right? But the outcome is going to be all sort of different along here, right? So this is a simplified version for you to go through and see. But what I want you to do is, so when we go through and we get a regression model, what we're going to have is like an ANOVA table that looks very similar to what we looked at before. It's all conceptually the same thing. Sum of scores regression, this is your sum of scores between, this is your sum of scores effect, like, right? How good is my predictive model? How good is my model at predicting just above and beyond guessing the mean for everybody? Sum of scores residual, this is my sum of scores error, my sum of scores within. Here's my predictive value or my group mean. How far are people different from the group mean? If I got a lot of error and I've got a lot of variability within groups, it means that maybe my grouping variable doesn't do a very good job of determining what my outcome is, because even within group, people are all over the place. We got very small within group variability. It means everybody who's in this group is all scoring about the same score, very little error, good prediction with that. Same thing here, okay? And so again, my model determined, the quality of my model determined by the ratio of my predicted to my total variability. What's my sum of scores regression over the sum of scores Y? That gives me my R squared, tells me the predictive quality of my model. All right, cool. Let's go through, take a break there, take 10, come back, and we'll jump into like the actual tests that we've got with it. Okay. So talk about, so the ins and outs estimation of our bivariate regression, our testing, right? Our inference test, how we go through and actually get p-values and numbers and things along these lines, okay? Really easy. This is what our regression model, our regression output looks like in SPSS. At the top, we have our model summary. Here we've got R. This is our multiple of correlation, okay? Multiple correlation doesn't have a whole lot of information in and of itself, but if we square our multiple correlation, that gives us our R squared, okay? This is our R squared here, so we would say that based on this model, X accounts for about 61% of the total variability. We've got a pretty good model here, right? Here we've got a standard error for R. We've got an adjusted R. We'll talk about that in a little bit, okay? Here's my ANOVA table, okay? I've got a sum of squares regression. This is telling me how much the variability that my regression model is accounting for above and beyond just predicting the mean, right? We got our degrees of freedom, we got our mean square, we got our F, and we got our p-value. Sum of squares residual. This is the sum of square deviations of my residuals, right? This is my error. And here's my sum of squares total. This is just my total variability in Y, right? So if I literally went to in SPSS and just asked for the sum of squares of Y, this is what it would get me. It's all just total variability, okay? Down here in my coefficient table, here's my constant. This is my A value. This is telling me that the expected value of Y when X is equal to 0 is 2.718. And my unstandardized coefficient here is 0.574. It says for every unit increase in X, I would expect a corresponding 0.574 unit increase in Y. Okay. Here's the standard error for my coefficients. Here I've requested a standardized coefficient, beta is 0.778. If I just got one predictor, what is this equal to? Is it Mandy? 0.778, yeah. What is this standardized coefficient equal to when I only have one in the one predictor case? What other statistic is this equal to? What's that? Okay, not the mean.
Variability? Error?
Pointing that again.
No,
It's slow.
it is my slope. What are we working with in problem set 1? Yeah, this is my Pearson correlation. This is my standardized coefficient, is just doing my Pearson correlation. What's 0.778 also equal to? In this, so output here. What's that? What do we start out talking about? Yeah. Right. Two squared, right? So with only one predictor, my standardized coefficient is equal to a Pearson correlation. It's also equal to my multiple R. So I take my Pearson correlation and square it. It's going to give me the same thing as my R squared, right? So just wanting you to go through and see in the one predictor case how all this stuff sort of goes through and corresponds and sort of works together. Okay. This all changes when we get into multiple regression, but for our basic regression model, everything sums to 0 with this. Okay. Here is my t-test for my regression coefficient and my p-value. Okay. So in terms of formula here, my degrees of freedom regression here is just equal to the number of predictors in my model. We only have one predictor in this model, so it's just 1. Degree of free residual is my total sample minus p minus 1. Okay, so I've got 24 people in this set. Minus 1 gives me 22. Degrees of freedom total is just the number of people in my sample minus 1. Here we go here. We already talked about how we calculate my intercept and my unstandardized regression coefficient, right? A couple slides back. This value, my standardized coefficient, this is just going to be my unstandardized coefficient multiplied by the standard deviation of x over the standard deviation of y. We're taking that unstandardized association and we're just standardizing it. We're just multiplying it by standard deviation of x over standard deviation of y. Do that, what it turns that into is a correlation coefficient in the bivariate case, right? And then the standard error of my coefficient here is just going to be the standard deviation of y over the standard deviation of x times 1 minus the square of my correlation over number of people in my sample minus the number of predictors minus 1. Okay. So, and then how do I get my t statistic? How do I get, what is a t statistic? You got a coefficient or sort of something over a standard error. If I take my coefficient divided by my standard error, get my t statistic. These are 1 degree of freedom tests. So it's just on a distribution, number of people in my sample, or excuse me, degrees of freedom total is where that's coming from there. Yep. Just the number of people in my sample minus 1.
Wait, so to get T, you said standard, it's your standard error divided by what?
Slope over the standard
Well, you got
error.
it, Gabe?
Wait, slope over the standard error?
Yep. So here's my statistic. Divided standard. Anytime you take a statistic divided by a standard error, gonna give you a test statistic, right? So here we've got an unstandardized coefficient divided by my standard error, gonna give me a t distribution. So my unstandardized regression falls on a t. Okay. My standardized coefficient, this falls on a different distribution. You get into this with some SEM stuff and you get different p-values for your standardized versus your unstandardized coefficient, not with here. You're always giving test statistics for your unstandardized coefficient. So, and again, remember that our standard error is giving us the stability, reliability of my sample statistic as an estimate of the true population parameter, right? Remember, our standard error is just the standard deviation of the sampling distribution. So if I took if I looked at the calculated this regression slope for the relation between X and Y, let's call it a sample of 100. And I did that for all possible samples of 100 with replacement that could be drawn from the population. What I would get is a distribution of those V values, right? My standard error tells me with a sample size of 100, how much that V value jumps around, right? It tells me how precise that is. And so if I've got a really precise estimate, it's dialed in, right? I'm gonna have a smaller standard error, I'm gonna have a bigger T value. If it's big standard error, it jumps around a whole lot, right? I'm gonna have a smaller T value, right? What determines what's the biggest thing that determines how much that statistic jumps around from sample to sample? Okay. Yeah, and so that error is what's jumping around from time to, or how far it falls from the actual population value. What's the thing that determines how much it jumps around?
Sample size.
Sample size. If I got a really big sample, I'm dialed in. It's not moving around too much. If I got a sample at 24, it's gonna jump all over the place. There are other things that will play in and sort of start to influence your standard error, but remember, it's the biggest thing, the biggest contributor is just your sample size. All right, so R squared, this is again proportion of variability of my outcome, right? Talked about our sums of squares here. My null hypothesis here is that my sum of squares regression is equal to 0, right? Or excuse me, that my R squared is equal to 0. This right here, my p-value for my regression in my ANOVA table, this is a test of my R squared. Okay. If my R squared is equal to 0, my sum of squared regression is 0. And so then this is going to be a really small f, and so this is going to be close to 1, right? As my R squared increases, my sum of squares regression is going to increase. So this, the test that we get in our output, this is a test of my R squared, okay? The null hypothesis here is that this model predicts 0 variability in my outcome, okay? So this test right here is testing the extent to which my R squared value is equal to 0. Okay, we'll see that. Okay. Here we have tests of my individual coefficients, right? This is a test asking whether or not my intercept value is equal to 0. Is this an interesting test? Almost never, right? I mean, there are circumstances, and I can set up a regression model to make this the primary test of my model. But in most cases, we could care less what the expected value of y is at 0. SPSS is going to give us a p-value for it. We just really often don't worry about it too much. But what I do want you to worry about is knowing what this is, conceptually what it means, and how to interpret it. Okay. Here is my test of whether or not my slope, my unstandardized regression coefficient is equal to 0, right? Note that this is a test of this value and not your sort of value right here.
Say that again.
Is it test my unstandardized coefficient, okay? To get my standardized coefficient, and we'll get into this, basically what we do, if I went through and took my data, so I've got raw X and raw Y, I regress Y onto X, and I get my coefficient here. If I went through and I created Z-scores for all my X's and Z-scores for all my Y's, and then regress the Z-score of Y onto Z-score for X, what I would get as my unstandardized coefficient would be this value. I've just standardized my solution, and so my unstandardized value would be equal to 0.778.
Which one do we care about more?
Well, we'll get into that. So it depends on what your goal is. The unstandardized coefficient is talking about this association, the predicted relation in units in raw units of whatever I'm measuring, right? So if I'm looking at the association between height and mass, this is really nice because it's saying for every, and let's say I've measured height in inches and mass in pounds. Say for every inch increase in height, I would expect this many pounds to increase by this much, right? That's something that's really meaningful and sort of has some meaning, right? But sometimes what we're doing is we're measuring things in psychological science with arbitrary scales that don't have any like real meaning, right? And so this can kind of be difficult to sort of look at, to know whether or not, and again, one of these things I always want you all to be thinking about in terms of practical implications and things along those lines. If I say, hey, I've got a standardized or an unstandardized coefficient of 0.003, is that big or small? Do you know? No, I don't know. It depends on the units, right? It could be massive, it could be trivially small, I don't know. My standardized coefficient, you can think about your standardized coefficients as falling along, they're kind of like, it's more like it's kind of like a correlation coefficient. In bivariate case, it is a correlation. In multivariate regression, you can get standardized coefficients that exceed 1 and -1, but some weird stuff goes on. But what it does is gives you a way in your regression model to compare relative strength of predictors across across predictors. And what we would interpret this, because this is very literally, this is the same version of this, except for here, we're saying for every 1 unit increase in X, we see a corresponding unit increase in Y. With my standardized coefficient, what I'm saying, for every standard deviation increase in X is a corresponding standard deviation in Y. So that's
Okay.
where the mean score.
So it's the same thing where like the raw score doesn't really tell us anything, but then once we standardize it, we're like, oh, this makes so much more sense now.
Yeah. It can, although Jalen, I would say that our this unstandardized coefficient, it's not like a sum of squares or something like that that's really hard, or a covariance that's hard to sort of know anything about. If I know what X is and I know what Y is, there's a lot of practical information that's in there. It's just this goes through and standardize it on a semi thing so that I can go through. So let's say in a multiple regression, I've got one predictor that's on a 0 to 1 scale and another one that's on a 0 to 100 scale. Coefficient for X and the coefficient for X2 are going to be orders of magnitude difference. I have no way of looking at that and knowing which one of these is carrying more weight in my predictive model. But if I go through and I request my standardized coefficients, I can go through and look. It kind of puts everything on the same scale, so it's easy to compare. All right, questions about this slide? This is a really important slide. You'll want to make sure that you understand sort of what's going on with this. All right. Johnny, for you, just kind of take a look at your output. Same stuff, just kind of in different spaces. Here is your R² value, right? Again, the null hypothesis is that R² is equal to 0. Here's your sum of squares with your model. Here's your F test from ANOVA. There's your P value right there. Here's your unstandardized coefficient for your predictor. Here's your intercept, right? Here's your standardized coefficient. The command is easy as reg Y, make sure you got your outcome on X1. And then the beta thing is just asking, if you leave beta off, it'll give you confidence intervals for your coefficients. If you put beta, it'll give you instead standardized coefficients. So, all right. How are we feeling about bivariate regression? Getting it okay? All right. Yes.
This is more of a logistics question. If we're only looking at one, thing, why is it called bivariate?
It could be dichotomous, I think. I know.
You got an X and a Y, so bivariate is.
So when we have like a t-test though, you don't call it like.
Yeah,
two t-tests.
some people call it univariate, like people will go back and forth with that, so.
So if I see univariate or bivariate, it's essentially the same
It's
thing?
Same thing.
Okay.
And it's very rare to see these types of models, because they're not terribly interesting, because I can just run it on a correlation, unless I want to have a predictive model. It's easy enough just to run this in a correlation, look at the strength of association here. What we do see far more often is going to be our multiple regression. Here, what we're doing is we've got a set of continuous and or dichotomous predictors trying to account for variability in a single continuous outcome. Okay, again, still wanting to go through and predict, but now the contributions of our predictors involve not only the association of the predictors with the outcome, but also the association of predictors with themselves. Okay, and this is where we start to get into some of that additivity things and stuff that we had talked about previously. Okay, multivariate regression, just a straightforward application of our simple multivariate GLM, right? We've got one outcome, we just use it in modeling a whole lot more predictors here. So I've got my expected value of y is equal to my intercept, plus weight for x1, plus weight for x2, plus weight for x3, so on, so forth. We have our error term here at the end. Now, my intercept is the expected value of y when all x variables, when all predictors are held constant, 0. If we take a look at our two predictor case, this is our most basic form of our multivariate regression. Here, in terms of notation, we've got y hat. This is our predicted score for y based on our model. This is our model implied score. This may be a good estimate of the actual observation. It may not be. It's just our predicted value. Okay. A is still our intercept or a regression constant, but we've got by1 given 2 and by2 given 1. This is going to be partial regression coefficient for y on b1 holding b2 constant. Same thing, partial regression for the coefficient of y on b2 holding b1 constant. Okay. And then E is our residual here. All right. And so what we've got is we've got x1 and we've got x2, and then we've got two coefficients that are sort of predicting this outcome. So this is the prediction of y by x1 holding x2 constant, prediction of y with x2 holding x1 constant. Okay, so these are just notations sort of noting different variables, which will become important in a minute, right? Now the magnitude of my predictors, right? The magnitude of my coefficients for each one of these predictors is going to depend on two things. The association of x1 with y and x2 with y, how tightly those two things are correlated, but then also the association of x1 and x2. The association, how related my predictors are with one another, starts to influence their relation with my outcome in this multivariate regression model. Okay, and the concept we get into multiple regression is this idea of partial coefficients. Okay, so again, going back to our simple two predictor case, we've got my expected value of y, my intercept, and then x1 predictor, x2 predictor, and my error. Okay, now this coefficient here for x1, this is the prediction of y with x1 controlling for x2. Okay, this represents the relation of x1 with y after everything associated with x2 is removed out. Okay, same thing, this coefficient represents the association of x2 with y after everything associated with x1 is pulled out. Where did we talk about last semester started to get into some of this stuff? People remember?
Partial, like beta squared and omega squared.
Yeah, partial eta squared, partial omega squared. That's exactly what we're talking about here, right? And what we start to do with multiple regression is we start sort of thinking about some Venn diagram stuff. How does this stuff relate after we pull out other stuff? This is why when I'm talking about regression, I'm always talking about the unique relation of x on y after we sort of pull everything, control everything else out. Okay. So as a consequence, what we have here is we can talk about this as partialing, we can talk about this as controlling, we can talk about things as holding constant. All of these things are essentially getting at the same idea, is it's sort of pulling out other variability to only look at the unique association of x and y. Okay, so if we look at this Venn diagram, like go through, start making these on your own. This is a really excellent way to try and sort of get your head around what's going on with these regression models. Okay, so here we've got an outcome, our y. Okay, and here we've got we're predicting y based on x1 and x2, and x1 and x2 both hold relations with y, but they also hold relations with one another. Okay, and so if we look at here, if we look at the squared correlation, or the squared Pearson correlation, looking at the association of y with x1, right? This is getting regions B and C. Gabe, can you tell, why can I, looking at this graph, why do I know that the association of Y and X1 is captured by regions B and C in here?
Because of the certain, yeah,
Yeah, it's just the overlap, right? Here's Y, right? And here's X1, right? If I'm just looking at the bivariate association between Y and X1, that's captured by regions B and C, right? Same thing if I'm looking at the bivariate relation of Y with X2, I've got C and D is covered with that. That's just the overlap of those two, right? If I want to look at the relation of the association of X1 and X2, I've got C and E right here, right? We're just identifying portions of overlap. Okay. But if I want to go through and I want to look at the proportion of variability shared between Y and X1 controlling for X2, now I've just got B here, right? Allison, why is that the case?
Because you're like taking X2 out of the
Right.
picture.
So if I go through and I take X2 out, X2 overlaps with X1, right? And so we've got region C here. That's part where X1 is related to my outcome, but it's also shared with X2. And so for my regression coefficient, my partial coefficient, X1 doesn't get to claim C because X, like, think about this, again, like you come to a party and I bring like a dip and some corn chips. That's what Abby brings. And then Daniela brings a different dip, but also some corn chips. No one gets credit for the corn chips because everybody brought corn chips. What's unique is Abby's dip and Daniela's dip to the party. That's what people get credit for. Anything that's shared, not saying it's not good. We're still all counting it towards the R squared at the end, but no one gets unique credit for it because it's shared and it's overlapping. Okay, same thing, my partial coefficient for X2, the relation of Y with X2 controlling for X1 is just region D right here, right? X2 is accounting for more than that on its own, but region C is shared, so no one individually gets credit for that variance component. But when we're looking at our R squared for this model, my R squared is B and C and D, right? My R squared doesn't care where it came from. All it knows is R squared is just capitalizing on corn chips, right? It's stuff that's accounted for. It's just not something that's accounted for uniquely by my predictors. Okay. What would happen then if I have a model? We have Y here. X2. X1. What's going on with this situation, Lindsay?
There isn't any overlap between X1 and X2.
So what does that imply about X1 and X2?
They're not related.
They're not correlated with one another. They're completely independent, right? And this is part of that additivity piece, right? Like I'm building a regression model where I've got X1 accounts for this piece of my outcome, X2 accounts for a completely different outcome. Piece of the outcome, there's no overlap. So we've got an incredibly efficient model right here, right? Could I have a model where I have an R squared that's quite large and no significant predictors? Yeah, what would happen? How would I draw that, Allison?
Your overlaps with. Can you say what you said again?
Yeah,
I know
I
that
have
the overlaps for one would be large, but not the other. Like
Okay, well, okay, so if I do this, okay, and this is X1, how could I have a large R squared and not have any unique predictors?
would it be that any overlap is also overlapping with Y?
Yeah, right. So if I go through and I have this, right, so I'm looking pretty good, but then I go through and toss in X2. And that's what X2 looks like. Now all of a sudden, I'm accounting for a big chunk of Y, right? So I've got a big R squared. But are either one of these predictors likely to come up as unique predictors of my outcome? No, I'm gonna get huge p-values for both of these. And I'm gonna be in a situation where I've got my model has a very low p-value, right? I have evidence that my predictors are accounting for my outcome, but I'm down looking at my coefficient table and I have no significant predictors, right? Well, it's because I basically put the same variable in there twice. The measure might say it's different, but it's actually not. It's all accounting for the same thing, right? And so this is where we have a maximally inefficient. Here's where we got a collinearity issue. That if we're screening properly, we should know that this is coming up before we even try to dump those two things in the model, right? So again, anytime we're working with a regression model, our coefficients are always always partial coefficients. Now, the thing we did before with the unique, where we have just two separate things that are uncorrelated. Now we've got a thing where our standardized coefficients for each one of those predictors that are unrelated, those coefficients will be very similar to my Pearson correlations in that case. That's generally not how things work in psychological science, because all the things we measure are related to lots of other things. And so we do get some overlap here. We're just trying to make sure that it's not collinear, that it's redundant, that it's the same thing. Yeah.
Is there any kind of like standard or rule of thumb for like what is too much overlap?
Yeah, that's a good question. It's something else, someone always people always want to know, like, so what's the thing? You got two different things. We've got statistically what's problematic, and then we have conceptually what's problematic. Statistically, you have to have predictors that are very, 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 very correlated before it'll crash the model. Your standard errors will get crazy and jump around. But the statistical model, the numbers will produce something. Conceptually, though, if I have two measures that correlate 0.8 with one another, are those two different things or are they the same thing? They're the same thing, right? And so that's where I need to start making conceptual decisions about which one's the better measure, which one should I probably get rid of, right? Sure. Because it's just, I'm building redundancy in my model and I'm making a weaker model for not using my sort of very smart or sort of conceptual brain and sort of throwing the same thing in there over and over and over again.
Sure.
Yeah. Other questions? All right, cool. So, oh yeah, what's up, man?
Can you give like an example of like what this would look like in the real world? Something that would be like overlapping.
Oh, I don't know, anything like take two variables and sort of like that are semi-related and sort of predicting an outcome, right? I want to look at
Would that be the same as like a mediator?
no, mediator is going to be a different thing. Okay, so hold on to that and we'll get to that stuff sort of in a minute. Okay, so here in terms of our formula for our multiple regression, okay, and this is just the two predictor case. As we start to layer on more predictors, it gets more complicated. But if I'm looking at the coefficient for Y, the prediction of Y based on X1 controlling for X2, here is just the correlation of Y with X1 minus the correlation of Y with X2 times the correlation of X1 and X2. Okay, so this should be, if you've started on any of the correlation coefficients, the Mang stuff, this should start looking familiar, right? Because what we're seeing is a coefficient that's dependent not just on the relation of my predictor with my outcome, but also the relation of my predictor with other predictors in the model. Okay, here, same thing, correlation of, or the coefficient for the association of Y with X2 controlling for X1 is in the in the two predictor case, derived from the correlation of Y with X2 minus the product of Y with X1 times X1 and X2 over 1 minus the square of the correlation of X1 and X2. My unstandardized coefficient for the associated coefficient of Y with a predictor controlling for other predictors is going to be the standardized coefficient times the standard deviation of Y over the standard deviation of X. Again, we move back and forth with standardization. And then my regression code, my multiple correlation, my squared multiple correlation is just sum of squared regression over sum of squared of Y. Or this is also kind of cool. If we go through it and think about my multiple correlation as just being the square of the correlation of my observed Y with my predicted Y. So again, in SPSS, if you save your predicted value and take the correlation between your observed Y and your predicted Y and square that correlation, it's going to give you the R squared for your regression model. Okay, so lots of different ways to kind of get at this and how do we think about these things, which makes some conceptual sense, right? If my if my regression model does a very good job of predicting my outcome, how should my observed Y and my predicted Y's correlate with one another? Very strong, right? And if I have a very high R squared, what does that mean? I got a very good model. If my model's no good, if it's predicted, it has little to no predictive relation, how would I expect my observed Y and my predicted Y's to correlate? Not good at all, right? And so again, just thinking about some of these statistics conceptually, kind of what they mean and how they work together can really help kind of deepen your understanding of some of this stuff. All right, so for a regression model, right? My multiple coefficient here, sort of the unstandardized coefficient for the association of Y with my predictor controlling for other variables in the model, interpreted as the expected change in Y given a unit change in X, holding all of the predictors constant at 0. Okay, so if we hold everything else at constant at 0, and I increase X by 1 unit, what's the expected change in Y? Okay. My standardized coefficient interpreted as the expected change in standard deviation units of Y given a standard deviation change in X, holding all of the predictors constant. Okay, so it's the same thing. Instead of just our units, we're going from with our unstandardized coefficient, we're talking about raw units. To our standardized coefficient, we're just talking about standard deviation unit change. Okay. And again, what's just going on in the math background of SPSS? When you request standardized coefficients, it's just going through and taking internally, not on your spreadsheet, but it's just taking Z values of Y, Z values of all your X's, and it's just regressing the Z values, Z scores for Y and the Z values of X, and it's giving you the same thing. Okay. Questions about partial coefficients?
Can you repeat what you said about like we're transforming the raw unit to standard?
Yeah, I mean, basically what's going on in the guts of SPSS when it's giving you standardized coefficients is just taking your outcome, calculating Z scores for that and Z scores for all your predictors, and then calculating like the Z scores for your Y and the Z scores of your X. So you can literally do this in SPSS if you just create Z scores for all your stuff and then take the Z scores and sort of create a model just with Z scores instead of raw scores. All your unstandardized coefficients will be identical to standardized coefficients in your other model, right? And so you can just kind of see how that all works together. All right. So for your multiple regression output formulas here, again, degrees of freedom regression in your ANOVA model is just going to be your number of predictors. Degrees of freedom residual, again, that didn't change. It's going to be total sample minus number of predictors minus 1. Degrees of freedom total, it's going to be the number of people in your sample minus 1. Now you're standardizing, this is just for the 2 predictor model. As you get into 3, things get more complicated. The 2 predictor model, your standard error for your regression coefficient is going to be the standard deviation of Y over the standard deviation of X. 1 divided by 1 minus the square of the correlation of Y, partial correlation of Y with X1 controlling for X2 over N minus P minus 1 over 1 minus the square of XY and X1, right? So we've got partial correlations sort of playing into this piece of things, okay? Now the standard errors for your individual predictors in your multiple regression, again, based on a couple of things. 1, how well do your set of predictors account for variability in your Y, right? Again, thinking about if I've got a high R squared, if I have a large R squared, what does that tell me about error in my model? It's small, right? And because my standard error is dependent on how much variability I have in that residual, if this is a small value, then my so the value of my predictors is, or my standard error is gonna be small, right? So how well your model is working and predicting your outcome is gonna impact the power of your test. Also the extent to which your predictor is redundant with other variables, okay? We're gonna talk about this in terms of tolerance, right? Tolerance is determined by 1 minus the squared multiple correlation of your predictor with all other predictors, okay? If I've got a variable that's highly correlated with all my other predictors in my model, I'm gonna have a high tolerance. What's gonna happen is I'm gonna have a lot of redundancy. I'm gonna have something like this. And what it's gonna happen is I'm gonna get large and unstable standard errors here, okay? Oh, note here, down here, that this notation, so in the 2 predictor case, the R squared for one, excuse me, up here. This is your multiple correlation down here. Sort of going into that calculation. So again, thinking about as I'm going through and building a regression model, let's say I've got a thesis or something along those lines, and I want to have small standard errors, right? I should be thinking about trying to have a regression model that accounts for variability in my outcome. And this is good for a lot of different reasons, but it's very good for power. So I might say, oh, hey, these are the things that I'm interested in actually testing and looking at. But what I should be doing is thinking in my head, what other things can contribute to this outcome? What are the other things that I can start to measure and include in here that are hopefully distinct and separate from the things I'm interested in? Thinking about, okay, what am I interested in looking at? What sort of piece of my outcome do those things account for? And then what's the other stuff that we're not accounting for? If I can measure that, include that in my model, what I'm gonna have is a much more powerful test, okay? Now where people go wrong is like, okay, well, I need to maximize my R squared. So what I'm gonna do is I'm gonna throw in, I'm gonna measure negative affectivity and depression and self-esteem and social support and I don't know, sort of these types of things. Fine, I might maximize my R squared, but what's that gonna do to my set of predictors? I'm throwing in things that are just globally associated with everything, and I'm creating redundancy in my model. And so, yeah, I'm sort of increasing variability here, but the problem is I've got a bunch of redundant predictors on top of one another, and that's gonna really screw my model over. Okay. Yeah.
Are every situations where like you care more about the predictability of the model rather than like what the variables affect the model?
I don't know, it depends, Gabe, where are you working and what are your aims, right? If I'm working in an applied sort of area, who cares, right? And this is where we get a lot of things like statistical regression and kind of black box stuff where I'm just throwing everything in the kitchen sink. Like, I don't care why it predicts, so long as it does predict, that's what I'm trying to do, right? Like the theoretical piece of this is irrelevant to me. I'm just trying to maximize the predictive ability of my model. Then in that situation, I don't care a whole lot of it, but that's never gonna fly in psychological science. Because I'm going back, why does any of this stuff make sense? It looks like you just threw a bunch of garbage in there and was like hope for the best. And probably what's happening is you're maybe predicting outcomes very well in this sample. But I don't know if this model generalizes anything beyond this sample, because there's no reason for these variables to be in there. So I don't believe your stuff. So you've done a cool trick with these data, but so it has no meaning to me, right? So that's the type of thing you want to watch out for. Yeah.
2 questions. One, so when we're looking at R squared in a multiple regression model, are we saying like X1 and X2 together are accounting for so much 62% variability in Y? Okay. Second question. For multiple regression, so 2 or more variables, right? So can they be dichotomous and continuous?
Yep.
Like
Yep.
1 and 2 can,
Yep.
okay, they don't look like,
Yep.
just as long as Y is continuous.
Yeah, exactly. If we got a categorical outcome, now we've switched over into logistic regression, which is super cool and we'll cover, but a little bit different. Yeah.
Okay.
I was gonna say, I was trying to figure out like in like a study such as like joy or happiness, like, what would be a better like sorry,
Additive.
sorry,
Yeah.
my French is coming out. Versus like redundancy. So I would think like, is it possible that saying that like having support from family would be more redundant versus like exercising, like what?
Yeah,
would
I mean,
that be?
it kind of depends, right? Like, so let's say I'm trying to like measure well-being, right? Maybe like I'm measuring income as a means of just like base needs, right? Like not that, I mean, I would expect that probably income has a non-linear relation with well-being. I mean, like the very low end, like if I can't cover basic things, then that's probably going to be problematic. I probably hit a certain point where it kind of levels off, so I would be worried about the linear function there. But like, so maybe so, okay, I have sort of big income, things like that, and then maybe I go through and I say family, right? Like, so family support, which doesn't necessarily, that doesn't seem like a collinear thing with income. You know, all sorts of family support and have very little wealth or a ton of wealth or anything between. I don't know, sort of that's kind of the thing, right? What I would start being worried if I say like, okay, now I'm gonna go through and I'm gonna include level of depression. Okay, well, that's fine, right? But then I also want to control for levels of anxiety. That's arguably not a different construct. And then I want to go through and I want to say like just general satisfaction with my job. And then I want to put in just general neuroticism as a personality trait. Now all of a sudden I've got 3 or 4 different variables that are probably all capturing the same thing. And sure, individually those will demonstrate an association with well-being, but I'm basically including the same thing. I'm just calling it different names, and now that's going to be problematic.
Yeah, that
Right. So, and so to something like well-being, there's like lots of different things that we can hypothesize are associated with well-being. They're sort of capturing different parts of this global construct that we might call well-being. And so interesting opportunities to sort of develop an additive model versus this is more an issue that happens to us clinical folks, is we just throw in like 7 different distress variables that are basically all measuring the same thing. And so what happens is, let's say I'm interested in looking at the relation of trauma survivors, the relation of PTSD with well-being, but now I throw in a measure of depression. And so now what my coefficient is looking at is the association of PTSD with well-being after I parcel out everything that's overlapping with depression. Well, I have to ask myself, well, what's PTSD without negative affectivity, depression stuff? I don't know what that construct is anymore. It's not the construct that I'm actually interested in. Now my model is going to tell me sort of this part of PTSD that's separate than negative affectivity, but if that's, I have to start thinking carefully about like sort of what I'm left with after I start sort of going through and sort of pulling things out. So, but that's not a statistical issue so much as a conceptual issue, thinking about like, what do I know about my constructs? What am I choosing to put in my model? All right, so in a multiple regression, going through, taking a look at stuff. Here, again, it's my R-squared value. Haley, you hit it right on the nose. This is telling me the total variability counted in my outcome that's being accounted for by the best linear combination of my predictors, right? Mathematically, we're saying, how do we combine X1 and X2 to maximally predict variability in my outcome, right? So this is variability in my outcome attributable to best linear combination or the combination of X1 and X2, things along those lines, right? This isn't unique variance, this is all the variability, right? R squared doesn't care whether it's unique or shared, it's just adding everything to the pile. Again, my ANOVA table, sum of squares regression, this is how well my model is, how well my model is predicting variability above and beyond just guessing the mean for everybody. Sum of squares residual is my sum of my squared residual. How much variability am I seeing between my predicted value and actual observed value? Sum of squares total is all the variability in Y that we're trying to account for. Right? My F test in my ANOVA table. This is again just this is my statistical test of R squared. Is R squared equal 0? This is what I'm getting at with this. My coefficients. Here I have my expected value of y when x1 and x2 are held equal to 0, right? Here is my unstandardized coefficient for x, holding x2 constant at 0. For every unit increase in x, I expect a corresponding increase in y. Same thing for x2, holding x1 constant at 0. For every unit increase in x2, I expect a corresponding increase in y. Here are my p-values. These are going to be my tests of these individual coefficients. Very literally, are these coefficients some non-zero value, right? So again, for constant, that's probably not going to be terribly interesting, right? But it starts to become relevant to thinking about, do I have evidence for a unique association of x1 with outcome controlling for x2 with x2 with outcome controlling for x1? These are our tests here, right? So in this situation, I have evidence for a unique relation of x1, but x2, not so much. X doesn't look like x2 is contributing to this model or bringing anything unique to the party, okay? If I want to take this outcome and actually write out my regression model, I got y equals 3.02 plus 0.561 x1 plus, oops, not plus, minus 0.00011 x2. So easy, just taking the coefficients from my model and building my linear equation here. Also, if I go down through and I take a look, so here's my correlation table, okay? I'm seeing, if I'm looking at correlations with X, this is just looking at my bivariate correlations. I see that X1 has a very strong association of correlation 0.78, right? So very strong association between my predictor and my outcome here. But if I look at X2, I'm seeing that I do have a correlation of 0.23, right? Which is in that smallish range. Now I don't have, I have a large p-value here. I can't say that there's an association, but I only have 24 people in this sample. If I had 100 people in this sample, would that, and that correlation stays the same? Is that going to be evidence for that association? Yeah, right. This is always the thing. I think correlations are a nice way to start thinking about the impact of sample size. I have a correlation of 0.23 here, and in this model with 24 people, I very clearly don't have evidence of an association between X and Y. If I turn this into a sample of 200, I absolutely will, right? Now, all of a sudden, this thing that, you know, if I'm not being careful with my interpretations, I'm saying, oh, this is unrelated to X, or this is unrelated to Y. Well, that's not true, or it might be true. It's just a null value, so I can't say one way or the other. And if I collected this in a sample of 200, I don't know, maybe that correlation goes down to 0. We know correlations are inflated in small samples. But if that hangs out and stays the same, now all of a sudden I've got a correlation that's associated with p.000000003, and I talk about like a highly significant. It's the same association we're seeing here. I'm just getting a much more precise estimate, right? So being very careful about not conflating p-values with importance, magnitude, things along those lines, okay? And this is the thing, if you ever start working with a big data set, I don't know, run a correlation table. If you got 400, 500 observations, everything's related to everything. You get correlations of 0.1 and it's correlated with stuff, right? So if you're just like p hunting, like it's all over the place, but it's all driven by sample size, right? So that's why we need to be careful in terms of how we're thinking about stuff. But then, yeah, see, we have an association of X1 and Y, or X1 and X2 correlated negative 0.5156. So there's a small association there, right? But if I go through and I take a look at my unstandardized coefficients, right? Remember in the bivariate case, these these standardized coefficients are equal to Pearson correlations. Here, that's not the case. These are now partial coefficients. But what I see here is I'm looking at the relation of my unstandardized coefficient for X2 with the Pearson correlation of X2 with Y. What am I seeing in terms of the difference there, Danielle. How does this value relate to that value?
So sorry, I was writing. Can you
No,
do that again?
yeah. So how does my standardized coefficient for X2 relate to my Pearson correlation of X2 with my outcome?
It's like taking into account X, Y. I can't remember.
Yeah. It's 0.11 here, negative 0.1 here, it's negative 0.23 here. What's happening is this association, everything that's shared between X1 and X2 is getting pulled out. So what you'll typically see, not always, we've got some suppression issues that will come up, but typically what you'll see is your standardized coefficient or regression will be smaller than your Pearson correlation, because in the Pearson correlation, it's just sort of everything that's overlapped. Here, it's overlap pulling other things out. So what you'll typically see is a smaller standardized coefficient relative to your Pearson correlation. And that's not always the case. Sometimes your standardized coefficient can be larger than your Pearson correlation. And then you've got an issue where you've got some suppression effects going on. And then that's a big thing to go through and try and solve. But in general, right, if we're thinking about correlated predictors in this multiple regression model, this is just pulling stuff out that's shared. And so we'll see a weaker association here than here. And we can see the same thing for your standardized coefficient for X1 relative to the bivariate. It's a little bit smaller. This is because anything shared with X2 is getting pulled out of that. So again, my standardized coefficient here, I'm not going to go through and worry about or interpret that because I clearly don't have evidence to make a call with one way or the other on this stuff, right? Well, what I could do is I could say this model is saying after holding X2 constant at 0, I would expect the standard deviation unit in X to be correspond to about a 3/4 standard deviation unit Y. Okay. So just same interpretation. We're just talking about standard deviation units as opposed to raw units.
So when we run a multiple regression, is that why we get like a correlation output, whereas we don't get that with a bivariate regression? So we look at.
I just added this in.
Oh,
This isn't part of your standard output.
Oh, okay.
I just dropped that in. All right, same thing, just in Stata. Again, easy regression, outcome, predictors. It's pretty simple statement there. So in terms of relative contributions, in your simple regression or multiple regression with uncorrelated predictors, right? Here, your standardized coefficient or your Pearson correlation, that's does a good job of capturing the contribution, right? In this situation, like if I just have one predictor or my predictors are correlated 0 with one another, which is never actually the case, but if it is, then each one of those individual standardized regression coefficients are the additive magnitude in terms of contributing to your outcome, right? But more often what we have is we've got correlated variables, right? And so what we need to do is consider the relation with my dependent variable, my other independent variables, and the unique relation with my outcome here, okay? And so we've got a couple of different variable or coefficients that we can go through and calculate within the context of multiple regression, okay? I've got the proportion of variability in Y shared with X, okay? So I can talk about this as the squared correlation of Y with my X variable, okay? Here in this diagram, this is AB over A plus B plus C plus D, right? This is looking at telling me the relation of X1 with my outcome, right? This region over all variability in my outcome here. Okay, this is just my squared Pearson correlation. People seeing this? Other thing that I can request is something we would call our semi-partial correlation. Semi-partial correlation is looking at the portion of variability in the Y that's unique to X, okay? Here, what I'm asking with my semi-partial correlation is what's of all variability, and make sure you write this down, of total variability in Y. In this model, what's unique to this predictor after I control for everything else, okay? And in this bivariate case, what I've got here is the ratio of region A to the total of A plus B plus C plus D. everything here, right? Of all variability in Y, what's unique to X1? Well, we've got what's unique total variability of X1 with Y is A and B, right? But here we've got X2 in the mix. X1 and X2 are related to one another, and so B gets taken out. B is shared with X1. A doesn't. X1 doesn't get credit for that as unique. So we're just looking at A relative to all the variability here. Okay, and this is my semi-partial correlation. But what I also have is a partial correlation. My partial correlation is asking what's the proportion of residual variance unique to X controlling for other predictors, okay? And here what we're looking at is the ratio of region A, because that's unique to X1, over A plus D, okay? Here, what we're doing is we're saying, we're not looking at what's unique of X1 to all of the variability in Y, we're looking at residual variability, okay? So once I go through and take out X2, which is the other predictor in my model, if I pull out everything that's related to X and overlapping with X2, now all I've got left over is A and D. Those are the only two regions I have left over. And of what's left over, what's attributable to Y or to X1? Now we've got A over regions A, D. Okay, this is what I'm getting at with my partial correlation. Okay, so here, what's the proportion of residual variance? Cross out unique, put attributable to X, controlling for Y, because of course it's unique because there's nothing else in the model, right? So of the residual variability, after I pull out shared variability with all the other predictors, I so put that aside. Of what's left over, what's attributable to my predictor, and this is my partial correlation. Now we'll have a Pearson correlation, a semi-partial correlation, and a partial correlation. If I square those, that's giving me a proportion of variability. Remember, you have to square those to interpret that way. If you don't, it's just a magnitude association. Okay. Where did we talk about residual variance before last semester? We were talking about partial omega squared, partial eta squared, same thing. Like that's what this coefficient is. It's saying after we sort of pull out variability that's attributable to other stuff, of what's left over, what's attributable to my predictor. Okay. So here, my squared semi-partial correlation, this is an intuitive index of an effect, right? Because it's easy for me to say, of all the variability in my outcome, what proportion of that is unique to Y after we sort of account for other things in the model, right? That's just kind of a nice way, an easy way to go through and think about things. My partial correlation, though, this isn't important for the calculation of powers and comparisons and things along those lines. We don't have benchmarks for semi-partial correlation, but for partial correlation, we can talk about small, medium, and large. And please, please, please don't just tell me something's a small effect, a medium effect, a large effect without contextualizing it in some way with some additional interpretation. Because again, we should never be just using these as hard and fast rules for stuff. But what we can have is with our partial correlation, some benchmarks to say this is generally kind of what we're talking about in terms of size magnitude here. Okay. Also note that your semi-partial correlation is identical to, or the formula for your semi-partial correlation is identical to your formula for your standardized coefficient, except just a small variation in the denominator. Okay. As a consequence, your standardized coefficient in regression can't exceed 1. So our correlations are bound by -1 and 1. A standardized coefficient can't exceed 1. But what you shouldn't do is ever, because you'll see this sometimes, is people will say what you do is you take your standardized coefficient and square that and interpret that as proportion of unique variability attributable to a predictor. Mathematically, you can't do that. You can do that with a semi-partial correlation. Don't do that with a standardized coefficient. Standardized coefficient is calculated just a little bit differently. Okay, but what you can do is use your standardized coefficient as a kind of a general magnitude of strength. You can kind of use that as an effect size. These are better, But once you start getting into more complex analyses like path models and SEMs and stuff like that, it's not a real good effect size for some of that stuff. And so what you generally see is people just using the standardized regression coefficient as a magnitude, a general magnitude of the effect. Last thing we'll talk about here real quick is our adjusted R. Okay. We know that our squared multiple correlation is positively biased, right? If I have, let's say I ask a question and I put together a regression model that literally predicts zero variability out there in the population, right? It's completely unrelated. So if I go through and I collect data from, let's say, a sample of 100 people and I run that model, in my data, is my R squared going to be exactly 0? No. And can my R squared be negative?
I don't think so.
No, because I can't predict negative variability. My R squared is always going to be some value. It's never going to be exactly 0. And the only way it can go is up. And so we know that our R squared is going to be positively biased. Now that positively, any chance fluctuations, any sort of residual error that starts getting picked up and the model is accounted for variability is going to be positive. And so what we're going to do is our R squared is a positively biased statistic, right? R squared is the same thing as eta squared, right? And we know that eta squared is a positively biased statistic. And so, and particularly if we've got small samples, right, this can start to become notable, right? And so what we've got instead is a formula for an adjusted R squared. This incorporates some correction for bias. This adjustment depends on the number of predictors you have in your model, or the ratio of the predictors to the sample size. The larger ratio of predictors to sample, the larger penalty we've got, right? So if I've got 15 predictors and 50 people in my sample, I'm going to get penalized huge for that versus if I've got 3 predictors and 60 people or something along those lines. Okay. Yeah.
So like, would that be related to like error in a way?
It's just bias, right?
Yeah.
So if R squared is functionally equivalent to eta squared, thoughts on what adjusted R squared might represent?
Omega.
So omega, right? It's functionally the same thing, right? And so this is essentially what this is. So your adjusted R squared is a better population estimate of your total predicted outcome. Now, for again, our adjusted R squared, again, it's not unbiased in and of itself, but it's better than R squared. Issue is like, if you're in statistics, Johnny, you've taken a lot of statistics in your classes with regression stuff. Did they sort of make a bigger focus on adjusted R squared versus R squared? Did anybody make a big deal about that?
We've always taught just to use R squared.
They just use R squared? Okay. If the goal, going back to your question, Gabe, is to predict variability in my outcome, if I'm just trying to predict whatever I'm trying to predict by hook or by crook, then I might be kind of concerned about R squared, right? Psychological science, people probably aren't going to be super, like that's rarely our goal. And so the people generally aren't going to be overly worried about whether or not your R squared is over predicting something. Like a lot of times sometimes people won't even report it, and you should always report that as a statistic. So it's not something that people get super caught up with. But just note that your adjusted R squared is probably going to be a better population estimate. But if you've got reasonably sized regression samples, the difference between adjusted R squared should be pretty minimal. Yeah, okay.
Is it relevant to adjust R squared in just a bivariate regression as well or not?
You can go through and you'll see an adjustment based on sample size. If the sample size is small, you're going to get a bigger penalty with adjusted R squared. So take a look at it, maybe note it. It's not going to be the biggest concern you have in terms of interpretations along those lines, but just wanting to let you know kind of where things are at. Yeah.
So when we are interpreting these, like in our problem sets, would you prefer that we use adjusted R squared since that's the population?
If you want to, if it's, again, with our stuff, like we're rarely worried about R squared is the sort of the biggest thing to interpret. But if you've got a real small sample size or a smaller sample size and you notice that there's a discrepancy, that might be a better thing to go through and report. All right. So some expanded output here. What you'll see with an SPSS, again, here's your R squared, here's your ANOVA table, which is your test of R squared. Here's your test, your individual coefficients, your standardized coefficients. But here what we've done is we've requested some effect sizes, some correlation coefficients here. And if you request part and partial correlations in SPSS, it'll give you the zero order correlation. This is just the bivariate association, Pearson correlation between your predictor and your outcome. Here's your partial correlation. If we square that, that's going to tell us the proportion of residual variability in my outcome that's attributable to the predictor after we control for other things, right? And here's my part correlation, which is my semi-partial correlation. If I square that value, it's going to tell me the proportion of total variability in my outcome that's unique to my predictor within this model. Okay, so note that SPSS, your semi-partial correlation, SPSS will identify this as your part, your partial correlation is your partial. Look at your semi-partial correlation is always going to be smaller than estimates of your Pearson correlation, your partial correlation, and this, right? Is the denominator is bigger. Your semi-partial correlation is total variability in Y. Your standardized regression coefficient, your partial correlation, is looking at residual variabilities, right? And so it's going to be, and then with the denominator change for beta, it's going to be a little bit different. So you'll see your semi-partial correlation will always be the smallest of these. Your Pearson or your standardized coefficient here generally going to be smaller than your bivariate correlation and larger than your semi-partial correlation, unless we've got some suppression things and then some crazy stuff can flip around. And really your relation between your standardized coefficient and your partial correlation, those two values are going to be really similar. It's gotten to a point where like I in a table won't report, I try not to report my standardized coefficient along with my partial coefficient or my partial correlation, just because they're almost identical values and it's just kind of redundant in there. So just kind of goes like that. Okay, so talked about those things. So yeah, for my semi-partial correlation here, if I square that, it's saying that after controlling for X2, X1 is accounting for 50%, 56% of the total variability in the outcome, right? Or variable X1 is uniquely accounting for 56% of the total variability in my outcome, whereas my squared semi-partial correlation for X2 it's like 1%, right? And it's a very large p-value, so I can't really say much of anything about it. Same thing for Stata, just going through and looking at your different P4, like the commands for these are super simple. All right, cool. We'll stop there. We're close to the end. Yeah, we've got a couple more. We'll just pick those up at the end and jump into this next stuff. Started to work through screening things. So, all right. Questions? You doing all right with stuff?
That was a lot.
That was a lot. That was